My name is KWood. I'm an electrical and biomedical engineering student. I'm enrolled in 311, 331, and 341. So this is my KI2 on audio amplification. Wow, I'm doing great already. So to start out, we had this amplifier circuitry where we had a sinusoidal signal coming in, biasing source to MOSFETs, a VDD, and then the output speaker, which we modeled as a resistor and a capacitor in series. We took advantage of the linearity and time invariance of the function and the transfer function h of j omega to get the output of the amplitude times the magnitude of h of j omega times cosine omega t plus the angle of h of j omega. I began evaluating the problem in Cadence where I built this circuit and then swept it through the frequencies of 1K to 5 megahertz and found the peak output voltages here. From this, I was able to plot them and then have a curve fitting operation to the transfer function alpha over 1 plus beta j omega. And then I got that alpha was 1.413 and beta was 3.627 times 10 to the negative 8th power. From that, I was able to plot the magnitude of h of j omega, where the alpha divided by the square root of 2 was around 1, and that was at the frequency of 1 over beta, 1.538 times 10 to the negative 7th. The phase diagram shows an exponentially decreasing phase, which is very close to the common emitter phase, which doesn't surprise me. So there's a lot of different ways that the Fourier series actually fits into sound amplification. First off, humans can only perceive variations in air pressure as sound if the Fourier series of the sound signal contains at least one sufficiently large term with a frequency of a range of 20 to 20,000 hertz. We can also note that there is a connection between how fast the Fourier coefficients go to 0 and how we perceive the sound. A pure sine sound has only one non-zero coefficient, while the square wave, which is the idealized version that I'll talk about in a little bit, Fourier coefficients decrease at 1 over n, which makes the sound a lot less clear. So for this, I found a naught to be 2.5 using this math, and found a of k to be sine of pi over 4k divided by 100 pi k. I then graphed it in MATLAB using this, as you can see here. Next off, we used coefficients and their relation to the transfer function to get the output voltage. And when I say transfer function, it's also analogous with frequency response. So for a of k does not equal 0, we got this wonderful equation. And then for a of k equals 0, it's fairly straightforward, and it's just the magnitude of the transfer function times the a naught value we found earlier. So now I want to talk about Gibbs phenomenon, where we were able to mathematically model the signal as this, whereas in Cadence it gave us this. I have a little animation over here that kind of helps to explain too as I go through this. So Gibbs phenomena essentially reflects the error inherent in approximating discontinuous functions by a finite series of continuous sine and cosine waves, where the partial sum of the Fourier series overshoots the function and it is approximating. The value of the time where the maximum overshoot is reached moves closer and closer to discontinuity as the number of terms summed increases, as you can see here. So once the overshoot has passed a particular time interval, convergence at a specific value of t is possible, which is pretty neat. So when we break the amplifier circuit down to a small signal model, we get this here. And you can see how the small signal model correlates exactly with the buffer amplification for current buffer you see here. So this source follower in this part actually acts as a current buffer, which I'm going to talk about. So the buffer amplifier is actually used as to transfer current from the first circuit, having a low input impedance level, to the second circuit with a high input impedance level. The buffer prevents the second circuit from loading the first circuit's current excessively and interfering with its desired operation. So in this case, it would be you get crappier sound amplification. In an ideal current buffer, In the diagram, the output impedance is infinite, and with an ideal current source, the input impedance would be 0 or act as a short circuit. Next, I'm going to move on to the anatomy of a speaker. The three things I'm going to point out is the cone, the coil, and the magnet. So the cone is moved by the coil, which is moved by the magnet. So as the magnetic field moves through, it moves the coil up and down, which then moves the cone up and down, which then changes the acoustic pressure and puts off sound waves that we can hear. Yeah. So now I'm going to talk about the hysteresis curve. So I'm going to basically camp out on rentativity and coercivity. So to start out, I'm going to show how see the y-axis is flux density, and the x-axis is the magnetizing force. And so why this is important at all is because to choose the best materials to get the best sounding speakers, you need to take the hysteresis curve into account for your magnet choice for your speaker that I showed you earlier, and the voice coil. So let's start out with talking about what even is hysteresis. So hysteresis is the lagging of the magnetization of the ferromagnetic material behind variations in the magnetized material, or magnetized field, sorry. The two most important factors we must consider when choosing a magnet for a speaker is the rentativity and coercivity, as I mentioned earlier. Rentativity is the ability for a substance to retain and resist magnetization, which is frequently measured as the strength of the magnetic field, and that remains in a sample after the removal of an inducing field. Where coercivity is the resistance of a magnetic material to changes in magnetization, equivalent to the field intensity necessary to demagnetize a fully magnetized material. Logically thinking, you can determine that the best speaker magnet would have the highest rentativity and the lowest coercivity value, as it needs to maintain its overall property of magnetization, but also must change the magnetization quickly to move the coil. The best coil material would obviously then have to be the opposite of the speaker magnet properties. It would have to be a hard ferromagnetic and the highest coercivity and lowest rentativity values. All right, made it in time. Bye.